Hi, my name is Oded Wertheim, and I'm leading the architecture at Quantum Machines. At Quantum Machines, we are building the quantum orchestration platform. It's a hardware and software platform which provides a way to easily and intuitively control quantum processors at scale. In this talk, I'll discuss the bottlenecks of variational quantum algorithms and how can they be addressed by hardware and software architecture. As quantum computers scale, the hardware and software performance should scale accordingly in order to realize the processor's true potential. Variational quantum algorithms, or VQAs, are optimization algorithms that attempt to find a trial circuit, or ansatz, that minimizes a cost function expectation value. Examples for VQAs include VQE, the variational quantum eigensolver, QAOA, quantum approximate optimization algorithm, and VQF, variational quantum factoring. The main components of VQA are a parametric circuit, a cost function that we want to minimize, and an iterative training procedure to find the optimal parameters. Let's examine VQA bottlenecks and ways to address them. These bottlenecks are common to various QPU technologies and architectures. The first bottlenecks we'll explore is repeated circuit execution overhead. VQAs require repeated circuit execution. Let's look at VQE as an example. In VQE, we measure the circuit in k different bases, paying the overhead for loading a modified circuit for each basis. For each basis, we then repeat the circuit n times to gather statistics, again paying the overhead for circuit execution for each repetition. This sums up to a significant overhead for each parameter set evaluation. Tight integration of classical computation eliminates most of the repeated execution overhead. Moreover, it allows to switch the order of the loops, avoiding repeating the same measurement back to back and improving the noise averaging. In the pulse diagram in front of us, we can see 3 circuits measured with 3 different bases. Each circuit includes an active reset phase, an ansatz execution phase, and rotation to the target basis and measurement. We can notice that the overhead for each repetition is eliminated, and the next iteration starts nanoseconds after the measurements of the previous one. Next, let's look at the overhead of circuit initialization that we need to perform on every circuit iteration. When using passive initialization, we need to wait multiple T1 periods until the qubits decay to the ground state. Active reset is a method that involves measuring a qubit and, based on its state, flipping it to the ground state. Using real-time feedback, a conditional pulse is played within 200 nanosecond latency. This significantly improves the initialization time. However, the fidelity is limited by the measurement fidelity. Can we do better? Yes, we can. Repeat until success provides a more sophisticated method involving running a repeat until success loop. We keep measuring the qubit and correcting its state until we are sure it is in the ground state by comparing the measurement to a second threshold. This method can reach very high preparation fidelities. However, it does not scale well with the number of qubits. An even more interesting method involves dynamic thresholding. The threshold in each iteration is determined by the qubit's history and is adjusted to optimize fidelity. The number of iterations is predetermined and the protocol requires only local qubit information, therefore scales to a large number of qubits. The reset fidelity increases with the number of iterations used in the protocol. The next bottleneck to consider is fidelity degradation due to parameters drift. Qubit parameters may drift during algorithm execution. Even though VQAs may have noise resiliency, the parameters drift may impact convergence time and the result fidelity. By monitoring the qubit parameters and perform fast calibration corrections, we can maintain high fidelity with a minimal time overhead. Another option is to jointly train VQA parameters and pulses parameters. For example, as we can see on the left-hand side, we can present to the VQA optimizer the pulse amplitude, its duration, and its phase. The two examples, measured in collaboration with LLNL and Q-control, present the ability to use the tightly integrated classical computation and active reset in order to significantly reduce the time for calibration and optimal control. On the left-hand side, we can see pulses calibration time reduced by a factor of 100 due to active reset and tight integration. On the right-hand side, we can see the measurement expectation value improvement by using active reset. The next set of bottlenecks are related to the classical and quantum computation interface. The first bottleneck relates to the overhead of updating the quantum computer with a new parameter set. The full parameters upgrade flow requires to compile the updated circuit, which can take a significant time, and then load the new circuit to the quantum computer. With parameterized pulses, we can skip the compilation and load only the new parameters directly to the quantum computer. The new parameters may be applied by frame rotations, updated pulses, or scaling the pulse amplitude and duration. The next overhead results from the classical computation performed sequentially on the measurement results. In some VQAs, classical processing is required on each circuit measurement. For example, cost function calculation in QAOA. Performing the circuit execution and classical computation sequentially implies that the total cost function evaluation time is the circuit execution time plus the cost function calculation time. Exposing a data streaming interface allows concurrent circuit execution and classical computation. This reduces the cost function evaluation time to approximately the maximum of the circuit execution time and the classical cost function calculation time, potentially reducing the overhead by half. Last, let's look at the overhead of executing multiple circuits, for example, of multiple algorithm instances. But first, let's look at the benchmark for VQA's throughput. CLOPS, circuit layer operations per second, was introduced by IBM as a mean to benchmark a quantum computer speed. CLOP represents the execution of 100 concurrent VQA algorithms updated with 10 parameter sets. CLOPS measures the overall speed and throughput of the quantum computer, resulting from both the QPU and control software and hardware performance. For each quantum processor, we can calculate the ideal clocks representing the processor speed when fully utilized. The actual clocks of the quantum computer is the QPU utilization times the QPU ideal clocks. First, let's look at a sequential execution of two VQA algorithms. On sequential execution, we get a significant overhead of the measurement data transfer to the classical processor, the classical computation, including the computation of a new circuit, the scheduling and loading time, and the circuit initialization time. Next, we can pipeline the classical computation and perform it independently for each algorithm. For example, we can find the next parameter set and compile the new circuit while other circuits are executed. Then, we can parallel the data transfer with scheduling and loading of a new circuit. A new circuit will be scheduled and loaded for execution once the previous one has completed execution. Next, as we've seen, we can significantly reduce the initialization time by using active reset techniques and dynamic circuits for multiple circuit iterations. And last, we can pipeline one algorithm execution with the loading of another, achieving a full pipeline execution. This required the quantum computer to maintain multiple concurrent contexts and efficiently schedule them for execution. We're working on the pipeline execution architecture to allow reducing the overhead and maximizing the QPU utilization. For summary, variational algorithms' performance may be limited by the classical quantum interaction. The QPU potential may be reached with the right software and hardware architecture. I invite you to come and hear our additional talks and visit us at our booth. Thank you.